Physical hardware degrades, network traffic spikes. To scale computing power continuously, we must decouple it entirely from the vulnerability of local machines. This matrix extracts 30 topics from 7 past exam papers to reveal a pattern. Mastering the highest frequency architectural models at the top of this list, specifically Docker, mobile cloud computing, GFS, and HDFS, secures the foundation to pass the exam. The core mechanism behind all these models is abstraction. Cloud computing is the practice of moving processing power, storage, and networking away from local hardware and accessing them remotely as services. This creates 3 distinct baselines of shared responsibility. In IaaS, you rent raw infrastructure. In PaaS, you receive the platform. In SaaS, the software is managed. None of this works without a specific engine driving it. Virtualization is the technology that splits physical servers into multiple independent virtual resources. This compares 2 virtualization structures. The Type 1, bare metal hypervisor, installs directly onto physical hardware for maximum efficiency. On the right, the Type 2, hosted hypervisor, requires an underlying host operating system. This extra layer consumes resources, causing a performance drop. Once the hardware is virtualized, cloud providers use multi-tenancy. This mechanism allows entirely separate tenants to securely share the exact same software instance without seeing each other's data. Abstracting the operating system provides the baseline. To fully understand cloud architecture, we have to track how engineers isolate applications, distribute storage, and push the network to the absolute edge. We start at priority 1 on the matrix, isolating processes and offloading heavy computation. Traditional virtual machines require their own complete operating system. Docker completely bypassed this limitation by creating containers. These are lightweight packages that bundle the application code and dependencies together, sharing a single operating system kernel. This diagram details Docker's client-server model. A user sends commands, build, pull, run, to the central Docker daemon. The daemon connects to a registry, downloading read-only templates called images. Issuing a run command spins those images into isolated environments known as containers. This strips away the overhead of separate operating systems, resulting in process simplification and rapid scaling. Docker isolates the application. Mobile cloud computing applies this exact same concept to the physical device. This schematic outlines mobile cloud computing's components: the mobile device, network, and cloud platform. The core mechanic is offloading. The system shifts computational tasks away from the phone to the cloud, preserving local battery life and freeing up limited storage. Traditional wired cloud computing assumes a stable, high-speed connection. Mobile cloud architecture handles cellular network constraints, automatically adjusting for sudden bandwidth drops and high latency. By isolating applications and offloading tasks to remote servers, architects successfully bypass local hardware limitations. The frequency matrix's second priority is managing distributed data across thousands of physical drives simultaneously. Google designed the Google File System, or GFS. They needed to quickly locate specific data fragments without crashing the network with massive search queries. This illustrates GFS data flow. A client querying a file contacts the master node. The master node holds no file data, only metadata, like namespaces, handing the map back. Armed with metadata, the client connects directly to chunk servers to read or write 64-megabyte chunks. Google's design was the basis for the open-source community's Hadoop Distributed File System, or HDFS. This table highlights exact exam terminology mapping. The GFS master node becomes the Hadoop name node. The GFS chunk server becomes the Hadoop data node. Pay attention to the architecture default sizes. While GFS breaks data into 64-megabyte blocks, HDFS uses 128-megabyte blocks to handle larger, continuous data streams. File systems organize raw data. To query specific data points within applications, we need cloud data stores. Traditional SQL databases are structured maps, requiring underlying operating system management. They struggle to scale horizontally. AWS answered this with DynamoDB. It's a fully managed NoSQL database. Storing data as unstructured key-value pairs, it scales automatically without hardware limits. Separating the metadata map from the data chunks prevents the central server from bottlenecking. The result is planetary-scale storage that retrieves data in milliseconds. Priority 3 explores how the cloud pulls real-world data through the Internet of Things. This maps the four-layer IoT architecture stack: perception at the bottom, then network, middleware, and application at the top. Data originates at the perception layer of physical sensors, moves up through the network, is translated by middleware, and transforms into analytics inside the application layer. To understand the hardware, we isolate that bottom perception layer and look at RFID technology. An RFID system requires three distinct components: a tag with a microchip and antenna, a scanning reader, and a back-end database to verify signals. This compares the tag types. Active RFID tags have an internal battery. Generating their own power allows them to maintain a much longer broadcast range. Passive RFID tags lack a battery. They remain dormant until a reader physically approaches them. The reader's electromagnetic field momentarily powers the chip to transmit data over a short range. For continuous environmental monitoring, architects deploy wireless sensor networks powered by the Zigbee protocol. Zigbee is heavily engineered for two strict parameters: exceptionally low power consumption and low data transfer rates, sending tiny data packets over very long periods. The exam tests a strict topological rule regarding this protocol. While a Zigbee network can have multiple routers and end devices, it can only have exactly one coordinator per network to maintain routing logic. Edge protocols like Zigbee and passive RFID sacrifice bandwidth to maximize battery life. They invert traditional computing priorities to survive in the physical environment. Priority 4 shifts to platform management, detailing how architects plan for inevitable system failures. Google App Engine exemplifies platform as a service, offering a standard environment for sandboxed instances and a flexible environment using Docker containers for custom scaling. GAE applications follow a 5-step lifecycle. Developers write the code, test it locally, deploy it to the platform, monitor its active scaling, and apply version updates dynamically. Microsoft Azure approaches platform management through this 3-part architecture. It splits tasks between compute and storage resources, managed by a central fabric controller. The fabric controller acts as the automated brain. It constantly monitors traffic and load balances virtual machines, ensuring applications stay online if physical servers fail. Infrastructure failure is an eventual certainty. Disaster recovery frameworks categorize these threats into 3 buckets: physical hardware failures, natural disasters, and targeted cyber attacks. This timeline graph measures business continuity. The recovery time objective, or RTO, is the strict time limit allowed to get systems back online after a failure event occurs. The recovery point objective, or RPO, looks backward. It calculates the maximum volume of data the business can afford to lose between the last backup and the moment of failure. By utilizing load balancers and strictly measuring recovery metrics, architects design for graceful failure. Systems are engineered to degrade smoothly and maintain core functions, rather than crashing entirely. This visualization tracks the next step in cloud evolution. To eliminate the latency caused by routing data across continents, centralized hubs are fracturing into decentralized nodes right at the edge of the network. These nodes are called cloudlets. They function as data centers in a box, deployed in local physical proximity to mobile users to handle high-intensity, low-latency offloading. The distinction is straightforward. Traditional clouds rely on massive global infrastructure, which introduces latency. Cloudlets rely on local hardware to deliver near-instantaneous compute. This diagram illustrates jungle computing. It takes a massive single computational task and splinters it across highly diverse, non-uniform devices at the same time. Standard server clusters require identical hardware to function efficiently. Jungle computing embraces hardware chaos, utilizing a smartphone, a laptop, and a grid server simultaneously to process the workload. Managing this level of decentralization exceeds human capacity. The solution is the Autonomic Cloud Engine, software designed to run the entire infrastructure without manual intervention. These advanced systems are programmed to follow the autonomic triad: self-managing daily operations, self-healing during disaster events, and self-optimizing to reduce energy consumption. Success in the upcoming exam depends on tracing this exact technological progression. From the initial layer of virtualization up through containerized deployments and planetary scale storage, ultimately, you are looking at the blueprint for a resilient system designed to survive at the absolute edge.